This is GCSE Physics Space Lesson 2. This one's star formation and life cycle. So, start activity. If you want to give an example of each of the following, if you want to pause and jot them down. So, an example of a dwarf planet would be Pluto, for example, or Ceres, or any of the dwarf planets that we discussed last lesson. A natural satellite, so you could pick any of the moons in the solar system. So you've probably gone for Luna, or the moon, the Earth's moon, which we simply call moon. And an example of a solar system. We did the definition, which is the collection of 8 planets and their moons in orbit around the sun, together with smaller bodies in the form of asteroids, meteoroids and comets. Alright, let's move on. So what we're going to discuss now is where stars come from, stars like the sun. So this is Messier 16, or more commonly known as the Eagle Nebula, or more specifically a certain part of the Eagle Nebula, which has been named the Pillars of Creation. So this photograph was taken by Hubble, and it's an active star-forming region within the Eagle Nebula itself. And stars are literally, it's like a factory for stars. They're literally produced inside these giant columns. Now, a bit more information about this picture. Any distinct blue colours represent oxygen, red is sulfur, green represents nitrogen and or hydrogen. And the pillars are illuminated by ultraviolet light from a cluster of young stars located just outside of this image. So the pillars of creation themselves, these pillars, stretch 4 to 5 light years in length, which means you would have to travel at the speed of light for 4 to 5 years. So the speed of light is 300 million meters per second every second for 5 years to get from one end to the other. So obviously that's quite a dramatic distance, especially for humans. But the entire Eagle Nebula itself will stretch, I think it's between 55 to 70 light years in length. Discovered by a Swiss astronomer, Jean-Philippe, all the way back in 1745, and it's around 7,000 light years from Earth. And if you've got a large enough telescope with optimal viewing conditions, and you knew where to look. Obviously, that's a big issue. If you knew where to look, you could probably see these yourself. But with varying degrees of resolution, obviously, to get an image like this would be impossible. You would need, something like the Hubble Space Telescope, which is what took this image. Anyway, let's move on. So around 4.6 billion years ago, in a galaxy not so far away as in our own galaxy, our sun started its life as a giant cloud of dust and gas, literally just floating in space, in a nebula, obviously which doesn't exist anymore, but in a nebula just like the Eagle Nebula. And the cloud, known as a nebula, not all of the cloud obviously, but a section of that nebula was pulled closer and closer together due to gravity. So all that matter that just floats around in space, gravity will start to act on it and pull it all in together. And, that mass will increase at quite a drastic rate. So, I've got a couple of images here. So as gravity pulls the gas cloud closer and closer together, what the particles will do is they'll start to rotate really fast, and it's a conservation of angular momentum. So as you can see the figure skater below, so she gives herself a little push as she brings her mass, inwards, as she pulls her arms in. She starts to rotate faster and faster. The same happens with the nebula clouds, as you can see on this animation in the top right hand corner. So as the gas starts to get pulled in, it starts to rotate faster, and as more mass gets pulled in, the speed will increase at an even more drastic rate, which will result in more collisions between the particles, which causes the temperature to increase massively. So the gas cloud becomes so hot and compressed that the hydrogen atoms can indeed begin to fuse together. So the fusion of hydrogen occurs at around 15 million degrees Celsius. So obviously really hot. For nuclear fusion to occur, you need drastic pressure and those drastic temperatures. So stars are, ideal for nuclear fusion. And nuclear fusion consequently releases a lot of energy. The sun, just a bit of trivia, the sun releases enough energy in 1 second due to its nuclear fusion to power the planet Earth for around 1,000 years in its current form. So a lot, but it's a lot. There's a lot of fusion occurring in the sun. You've got thousands of tons of hydrogen being fused every second. So our sun's quite boring. It's not really very special. It's an average star in the middle of its life. We call that the main stage of its life, or the main stable period. So, a star's created from a nebula initially, or part of a nebula, and everything's pulled in by gravity. The gravitational field of the sun, even at the surface, is around 242 meters per second squared, compared to the Earth's, approximate 10. So a good question is, why doesn't the sun just collapse due to its gravity? So the sun is stable, or well, any star really is stable, because the force of gravity that's pulling it in is in equilibrium with outward forces and pressure due to the nuclear fusion that's trying to expand the star. So you've got two forces acting. You've got outward pressure, or outward forces due to the nuclear fusion, and then pulling it in, you've got the gravitational force. Eventually the gravitational force will win, but we'll discuss that in the subsequent lessons. So a stable star. For a star to be stable, the forces must be balanced. So you get gravity inwards, fusion outwards. And for any stable star, the inwards force due to gravity must be equal to the outwards force due to fusion. So if you want to pause and make some notes or draw that image, that's fine. Let's move on. So equilibrium. We say that stars with balanced forces are in equilibrium. Stars in equilibrium are said to be in the main sequence period of their life. And Robert Hooke, which is Mr Kirkham's favourite scientist, stars usually spend about 10 billion years in equilibrium before they die. So the sun's, 10 billion years. It's about halfway through, 4.5 billion years. So it's still got quite a long way to go. In subsequent lessons, we're going to look at the life cycle of stars. So it's quite a good overview of this, actually. I'll probably come back to this. It's got star-forming nebula, protostar. Then depending on the mass, if it's a lowish mass, for example, like our sun, it'll take the top route, main sequence, red giant, planetary nebula, white dwarf. After that, you've got a black dwarf. We'll discuss that as well. If it's a large star with high mass, a different type of main sequence, burns hotter, doesn't burn as long. Red supergiant, supernova explosion, they're really interesting. We'll discuss those. Black hole or neutron star at the end. So I look forward to doing that one. Right, let's do some questions then. So if you want to pause and do these, and then we'll look through them. Right, so number one. So a lot of these I'll probably do spoken. So is our sun a large star? No, it's pretty average, to be honest. So I'll just say no. Are they all the same size? Definitely not. No. How do stars form? I'll stop moving about, that's a bit annoying. Right, number two. So how are stars formed? So you got a nebula. And in that nebula we have gravity. Gravity will act. Obviously, if you're writing this in an examination, you need to use coherent sentences. So nebula, gravity, pull it all together. Pull together. Speeds up, gets hot, etc. So how hot is this typical star? You're looking around 15 million degrees Celsius. That's it. That's near the centre. Surface temperature of the sun, for example, is around 6,000 degrees Celsius. That's the actual surface temperature, which is obviously still very hot. Number four, so if you pick this one up, so what element makes up most of a star's mass? Hydrogen. Hydrogen is obviously 1,1. Single proton with an electron, and it is the most abundant element in the universe. 5, what is a nebula? So you kind of define that as a stellar nursery. I actually didn't say that. Maybe I should have done. So where stars are born? Big cloud of gas. So the one that we talked about earlier is the pillars of creation contained within the Eagle Nebula. And it's where stars are made. 6. What is required for nuclear fusion to take place? Lots of mass, pressure, and a lot of heat. So I'll just write temperature. Number 7. Why doesn't the sun collapse in on itself under its own gravity? That's the equilibrium condition. I'll just write. That means equilibrium. And we've got pressure being balanced. The pressure due to the nuclear fusion being, or counteracting the gravitational force that's trying to crush it. Why does the sun remain at a constant size? Exact same reason. You know that the constant conversion of the hydrogen within the sun's due to nuclear fusion, creating massive amounts of pressure acting outwards. And the sun, you know, an average star's got enough fuel to keep it going for a long period of time in that main stage or main stable period. And then finally, how long does the average star shine for? So that will Mr. Robert Hooke at the end. Around 10 billion years. And our sun is around 4.6 billion years old. So around halfway through. Anyway, thanks for watching. I hope that helped. And I'll speak to you soon.